or an ionic compound? Well, the first element will tell you this is a metal. So if you look at your periodic table, you'll see that iron is a metal, and it is in fact a transition metal, which is important because transition metals are special. When we name them, we don't just write their name and then chloride. We have to add an extra step. We got to figure out what the charge on the transition metal is. And to do that, you can do that a couple of ways. This time I'll show you we can do reverse crisscross rules. So up here I'll write iron chloride. Well, you ask, where did these subscripts come from? Well, we have a rule called crisscross rule, and so if a 3 ends up down here, it's because it came from a charge that used to be on iron before we did the crisscross rule. So iron has a charge of 3 plus, chloride has a charge of 1 minus. You could double check that. Chloride it needs to gain 1 electron in order to be like a noble gas. So it should have a charge of 1 minus, and that matches up with the reverse crisscross. Okay, so that is how we know that the charge on iron is 3. That number 3 goes in as a Roman numeral, and here's something that you should really watch out for, is that 3 means that iron has a charge of 3 plus. Does not mean that chloride has a subscript of 3. It means that iron, the metal, the transition metal, has a charge of 3, and that's because iron is a transition metal. Its valence electrons are all mixed up into d orbitals, and there's a lot of overlap going on. So we need to say, well, that's the charge on this metal. Otherwise, it can form different charges, and we're not positive what kind of charge it's going to form. We just know it's going to be a positive charge, but not what the number is going to be in front of it. Okay. Now, another example would be if we come across something that starts with a nonmetal. So this compound right here, we start off with a nonmetal, so it's going to have a different list of rules. We're going to be naming things using our molecular compound rules. So we have to use prefixes. Starting with the very first element, we name that element normally, and then the second element we add "ide" to the end of it. So hydrogen gets turned into hydride. And then we're not done there yet. We need to add prefixes. So that's the difference between molecular and covalent ionic, is we need prefixes to say how many there are. So the prefix for 2 is di, and then for 6 is hexa. So this guy is dicarbon hexahydride. In terms of exceptions to any of these rules, if there was 1 carbon, we wouldn't say monocarbon, so watch out for that. If there was 1 hydrogen, we would say monohydride, because you only use mono on the second element. So don't forget that rule as you're working on the exam. Okay, moving on to dot structures. So we looked at dot structures for ionic and molecular as well. We looked at for both. So what's important with ionic compounds is we need to see that transferring of electrons. So I'm going to draw this as an example. To draw a dot structure, we need to look at the number of valence electrons in each of the atoms in the compound. So sodium chloride has sodium and chlorine in it. Sodium is in the first group, and it's got a 3s1 electron. That's its valence electron. So its outermost electron, there's only 1 because it's got 1 electron in the 3rd energy level, and it's in the first group. So it's got a 3s1 electron way out there. Chlorine, it's in the 7th representative group, and if you look at its valence electrons, if you look at its electron configuration, the ending for chlorine's valence, for chlorine's electron configuration is 3s2, 3p5. So 3s2, there's 2 electrons there, plus the 5 from the p orbitals. So there's actually a total of 7 electrons. Okay, and because chlorine is a non-metal, non-metals this side of the staircase, they want to gain electrons to be like a noble gas, and metals on the other side of the staircase, sodium wants to lose an electron to be like a noble gas. It's closer to being a noble gas if it loses an electron. So to form an ionic compound, transfer an electron. Okay? So when sodium chloride forms, chlorine has 8 electrons in its valence shell. Sodium's only left with the inner electrons. So you don't see any valence electrons. The inner electrons are there, and that makes it more stable. Let's look at a molecular compound. So drawing a valence electron, drawing a electron dot structure for a molecular compound is a little bit different. We're going to be sharing electrons. So the dot structure ends up looking a little bit different. So a good example of this is NH3. If we pronounce that using our naming rules, it would be nitrogen trihydride. And the first step would be we want to count the total number of valence electrons. So nitrogen, it's in the 5th group. So it has 5 total valence electrons. Hydrogen is in the 1st group. It has 1, but there are 3 of them. So it's going to be 5 from nitrogen and the 3 from hydrogen. We have 8 electrons to place. Okay, so this is a different step from what we did in the ionic compound. So we have to bond these things together. Nitrogen's the central atom because hydrogen can never be the central atom. So by default, in this case, nitrogen is the central atom. So the next step here would be to bond everything together, single bonded, and then make sure that you place all your electrons. So if you don't use up all of your 8 electrons in the bonds, then you have to place unshared pairs. So 8 electrons total, we've only used 6, so we have to add 2 more, and we're going to start at the central atom. Okay, and if you look, hydrogens only want to share 2 electrons, so these guys are all